morning. Today we are going to talk about linear models. When you say linear model or linear regression, most people think about simple quantitative model with two numerical variables, y versus x. In this example, we have a group of mice which are fed different food with different calorific input, and after a while we measure the body mass, and the result is shown here. You can make this scatter plot, and you can then fit a straight line through your data according to this model. The model is written like this, where response y depends on the predictor x. This is the terms we are going to use, predictor and response. Beta naught and beta 1 are coefficients of the fit. In this particular case, beta naught is intercept, beta 1 is slope. And at the end, we have a residual term, a noise term. Residual is simply the difference between the best fitting line between the model and the data. In order to find the fitting coefficients to fit the model, we minimize this quantity, which is the sum of squared residuals. Let's do this in R. We prepare data set containing kilocalories. This is the calorific input and mass, body mass of a mouse. Then we type LM, which stands for linear model. The first argument is the formula, and the formula in this case is mass versus kilocalories. This is our response, this is our predictor. And we specify which data set we want. We code it MS. After the model has been created, we can plot, or we can print its summary. There are lots of things printed here. I will explain them in details later. Right now, you can just notice these estimates and errors. These are our model parameters, model coefficients. There is an intercept, which is 20 plus minus 0.8, 0.9. We can write it down as beta naught is 20.2 plus minus 0.9, and kilocalories, which is 0.4 plus minus 0.1. This is our slope, intercept and slope. A simple quantitative model is useful, but in biological sciences, you deal much more often with categorical data. In this example, the predictor diet is a category, a normal diet or a high-fat diet. This is more typical experimental setup where you feed your mice two different types of food and then measure the body mass. I will teach you how to build, understand, and use linear models for categorical data. We start with these 5 equations. In each equation, we say that the response is the sum of mean, mu1 or mu2, plus a noise term, where mu1 and mu2 are true unknown means of populations with normal diet and high-fat diet. Now we take these 5 equations and transform them into something more useful. First, we rewrite them in explicitly symmetric way. So we can see both mu1 and mu2 in all equations. I simply multiply it by 1 where there is mu1 and 0 where there is no mu2, and vice versa. Then we can simplify it using matrix notation. For those of you who are not familiar with matrix notation, in the middle we do multiply 2 matrices. We multiply matrices rows by columns. So the first row in this equation will be y1 equals 1 times mu1, 0 times mu2 plus epsilon 1. This is exactly the first row here, and we follow for all the rows. You can write it down even in a much more compact way using symbols. Y equals w mu plus epsilon, where these are vectors and matrices. W is a design matrix. The design matrix contains only zeros and ones. It's a selection matrix. It tells you which measurement or which response belongs to which group, the normal and high fat diet. And this is the selection matrix. If we had more groups, there would be more columns in this design matrix. Now I'm going to spoil the simplicity of the linear model and make things a little bit more complicated. We are going to use contrasts. A contrast is a difference between two group means. Beta 1 is a contrast, is a difference between mu2 and mu1. Beta naught, on the other hand, is an intercept. We take our original 5 equations and we replace mu1 and mu2 with beta naught and beta 1. And then again, we can write it in a matrix form. I skipped this step with explicit symmetry, but I hope you can see how it works. Every equation contains beta naught, the intercept. So the first column in this matrix is always 1. The second column is a selection of beta 1, where we have a high fat diet. So 0, 0 for the first two equations and 1 for the rest. Again, we can write it down in a very compact form. And X is also a design matrix, just like W was a design matrix before, but it's a different design matrix. It contains intercept and contrast, while the previous design matrix corresponded to each mean of each group. These two equations are completely equivalent. They just show you a different look at the same data. R contains a tool to create a design matrix in a very easy way. First, we create some data. It's the same data you saw a moment ago. There is a diet, normal and high fat, and there is some body mass. In this line of code, what we do is we order the diet in a specific way to make sure that the level norm is the lower level and high fat is the next level. What we use is a function factor. We turn a variable into a factor. This is not really a place to teach you about factors in R. If you are not familiar with this, I strongly recommend to read a tutorial about this. But very briefly, a factor is a categorical variable with a few possible values or levels, as they are called in R. And these levels have a specific order. So our diet is a factor with two possible levels, norm and high fat, and the norm is our reference. And then we can create a model matrix using a formula mass versus diet. This is the matrix with intercept and contrast. If you add a 0 in the formula in R, you specifically change it into a format with the first mean and the second mean. Again, these are two alternative approaches to the same data. This is how we create a linear model in R. First, the case with intercept and contrast. This is our basic formula, mass versus diet. We are using function LM, linear model, and we specify data, which is created in the previous slide. When you type summary of F1, you will get a brief description of this model. Specifically, you find intercept and the coefficient diet high fat, the values, and the standard error. That means that the intercept is about 19 plus minus 4, rounding up this properly, and the diet high fat, which is our contrast beta 1, the difference between the two groups is 13 plus minus 5. If you add a 0 to the formula, you tell R that you want an alternative approach with a design matrix specifically showing the mean for each group. There is no intercept and contrast. The result is simply the mean of the first group and the mean of the second group. Be careful, as the naming convention in R is quite confusing. In both cases, the second variable is called diet high fat. It's built of the name of the variable diet and the second level value, high fat. However, In the first case with contrast, that represents a contrast, the difference between the means. In this case, it simply represents the mean of a diet high fat. The same name, but two different meanings. Be careful which one you use. The figures on the right visualize model coefficients. They show experimental data as points. The short horizontal bar corresponds to the mean of each group. In the top example, we use intercept and contrast. The intercept is the mean of the reference group, and we specified by ordering factors that the reference group is the normal diet. This is the mean of normal diet and is then represented here as the dotted line. This is our reference. The contrast diet high fat is the difference between mean of the second group and the reference. In the second case, each coefficient is simply the mean of a given group. What about p-values? What do they mean? This time the figures on the right show directly model coefficients and their standard errors. In this case, we have intercept and diet high fat, which is 19 plus minus 4. This one is the first one, and about 13 plus minus 5. This is the second one. Numbers in plots represent p-values 0.015 and 0.074. The null hypothesis in each case is the same, but the effect size is 0. We can see that intercept is quite far from 0 in terms of its errors, hence the p-value is small. The intercept is significantly different than 0, but this information is usually not very important. What is more important, that the diet high fat, which is our contrast between the high fat and normal diet, is not statistically significant. The p-value is not 0.07. This is not far away from 0 to call it statistically significant. In the second case, it just tells you that both means are statistically significantly different than 0. I would say this information about the contrast is more useful. Why do we call this a linear model where we have categories? Well, because it is a linear model, and you can imagine the following representation. We replace diet, normal, and high fat with numbers 0 and 1, like in our dummy variables. And then we can fit a straight line, just a normal regression model using this formula, using the intercept and the slope, and they come from our model. However, this is not the great representation because our predictor is categorical, not numerical, and it really doesn't matter what the value of the response is in between them. So this just shows you that this is a linear model, but it's not the greatest representation. Actually, just forget about it. It is a t-test. We have a simple experimental setup where we have only two groups. And then in this case, the linear model directly corresponds to a t-test. If you perform a t-test on the same data, specifying that we request for equal variances, in a function t-test, apart from giving an x and y vectors, you can also give a data table and specify the formula. This is the same formula we used in the linear model, and the result would be the same. This is the result, t-statistic, number of degrees of freedom, and a p-value. If you apply the model with contrast, this is the same t-value and the same p-value. There is just a negative sign because t-test treats it in the opposite way, but it doesn't really matter. The t-test also gives you the mean of each group, which are the coefficients in the alternative approach with means, not with contrasts. Results are the same. Now it's time to see how to include multiple variables in a linear model. We have a new data set now, where in addition to the diet, we also record sex of a mouse. The plot shows our data, and there are 4 categories here. Normal diet female, high fat female, normal diet male, and high fat male. As always, I strongly recommend to make a plot like this before you start analyzing your data. just by looking at it, you immediately see that there is some effect from a high-fat diet. The formula we are going to use in R is a simplified version of the actual mathematical formula where we simply skip the intercept. We always skip intercept in formulas in R. Our formula would be consisting of two factors, x1 plus x2. In this case, that would be diet and sex. And the mathematical representation of this is as follows. There are three coefficients, the intercept beta 1 and beta 2. And these vectors, x1 and x2, they are dummy variables. They contain zeros and ones. They are selecting variables. They select rows from your data which contain the given category. And they correspond to columns in the design matrix. This is the design matrix. The first column is the intercept. It is always 1. The second column corresponds to the diet. This is a low-fat diet or normal diet and high-fat diet. And the third column corresponds to sex, male and female. Let's generate some data. We create data frame in R. We call it MDS, and it contains mass, diet, and sex. The important thing, we have to again specify the order of levels in each categorical variable, because the first level would be also considered as the baseline or a reference. In this case, we set diet in the way that normal diet is our reference, and we set sex in the way that female is the reference. These are the first levels of the factor. We can see the model matrix using our model.matrix function, and it looks exactly the same as in the previous slide. Then we can use our function LM using the formula mass versus diet plus sex. This is our linear model formula. And when you type summary of F, R will print a simple table containing results. The table below shows the explanation of this table printed by R. The first coefficient is the intercept, beta naught. Its value is 19 plus minus 2. That's the estimate and its standard error. This is the mean of the reference. And the reference, because we set levels of our variables, the reference is diet normal and sex female. Then we have the effect of diet high fat. Beta 1 is 13 plus minus 2. And finally, the effect of sex male, which is 2 plus minus 2. You can see this effect is not significant. The p-value is large. You can also guess it from here. When you compare it to 0, when it's 2 and a standard error is 2, then probably it's not significant. This is how R names these variables. It combines the variable name, diet, and the level, high fat. The variable is sex here, and the level is M. You can make a figure showing how the fit coefficients work. We have the reference. Again, it's a diet, normal, and sex female. This is the intercept. And then this is the effect of diet high fat for females. This is the effect of sex male for normal diet. And this is the combined effect of diet high fat and sex male. So you have two effects away from the reference. And this yellow line is simply the sum of these two effects. We assume that the effects are additive. That is, when you have a group where both diet and sex are changed with respect to the reference, the two effects act together in a linear fashion. You can notice that in this figure that our model is not perfect, because the model, when you add these factors, the model does not represent the mean of each group perfectly. There is a small difference, a small offset. This is because we do not take interactions into account. Now, in this model, we take interactions into account. If you remember from ANOVA, ANOVA produced a model with interaction that showed you each coefficient and the interaction between them, and I discussed this in details before. If you want a model with interactions, you specify your formula like this: mass versus diet plus sex plus diet colon sex. This is the interaction term. And in the model matrix, you see that the interaction term is 1 here when both diet is high fat and sex is male. In the mathematical description, that will be a mixed term containing both variables and a coefficient beta 1, 2. The result of this model with interaction contains one more row. This is the row for interaction. And the figure shows that now the model describes data perfectly. We have exactly, each model coefficient adds up exactly to the mean value. However, the interaction is not significant. The value, the p-value is quite large here. Just like in ANOVA, interaction means that our subjects respond differently to the combination of the two variables than they respond to individual variables. An example of an interaction would be when males and females respond to diet in a different way. It is an ANOVA. A linear model with just two groups corresponded to a t-test. A model with multiple groups corresponds to an ANOVA. And we can make a plot, a familiar plot, where columns correspond to the diet, normal and high fat, and the rows correspond to the sex, male or female. You have seen plots like this before. Below, there is a formula for ANOVA, which is very similar to our linear model formula. The only difference is that the reference here is the grand mean, which is the mean across all the conditions. In the linear model, our reference is one specified condition. In this case, it was a female norm. That's only difference. If you perform ANOVA on this, this is the result you get. You get effect of diet, you get effect of sex. And again, the model will tell you that the interaction between diet and sex is not important. It's not statistically significant. I need to briefly explain what R squared means. If you create a linear model and ask for a summary, it gives you lots of things. And among them is this, R squared or adjusted R squared. What is it? R squared represents quality of the fit. It is a 1 minus variance explained by the model divided by the total variance. The variance explained by the model is given by this equation. It's the response minus the model squared and summed, and variance, total variance, is the response minus the mean squared and the sum. You can see this in this figure where the model fits data very well. The contribution to variance explained by model are these short continuous lines, solid lines, while the total variance is represented by the sum of squared dashed lines. This is the mean, this is the model. Model, the data follows model very nicely, but the variance, total variance is much bigger. In this case, variance explained by the model is very small, total variance is larger, and R square is large, it's 0.97 in this case. On the right-hand side, we have a case where variance explained by the model is similar to the total variance. These residuals are very similar to the total variance. In linear models, apart from R square, you will get also adjusted R square. This is what you should be using. It takes into account number of model parameters. Let me finish this lecture with a worked example. We are going to use a publicly available example data set, which come with many libraries. In this particular case, we need a library called CAR. It has nothing to do with automobiles. It stands for Companion to Applied Regression. And it contains some example data sets and also useful functions. After installing, we can call this library, and there is a variable, there is a data frame called salaries. These are first 6 rows of this salaries data frame. It contains data from 2008, 2009, 9-month academic salary for assistant professors, associate professors, and full professors in a college somewhere in the United States. The data contains the rank, professor, assistant, and associate professor, a discipline. There are only two groups here, A and B. A is for theoretical departments, B is for applied departments. Years since PhD, years of service, sex, male or female, and a salary in dollars. When you analyze data like this, I always suggest, again, make a plot. Look at your data first. This is a very simple plot that shows salary versus all of our variables. Salary versus rank, assistant, associated, and full professor. You can immediately see that full professors earn much more. There is a discipline, there is some difference. The applied disciplines seem to give you slightly better salary. Years since PhD, years of service, and sex, female and male. A question which is often asked, is there a gender pay gap? We can create a model of salary versus sex for our data. And when you run this model, it will tell you that the coefficient sex male, in this particular case, female is the reference, is statistically significant. Males earn about $14,000 plus minus 5,000 more than females. However, this is a very simplified model, and you can see chi-square here is not 0.01, which tells you that the effect of this model is essentially random. It's a very poor model. It doesn't describe your data correctly. What you need to do is to use a proper multivariate model. You have to include all our variables in the model. And then you have lots of responses. You can see the effects of various variables. For example, the very strong effect, the p-value is very small, of the rank of full professor. It tells you that the full professor earns about $45,000 more, plus minus 4,000, than the reference. Discipline B, the applied studies seem to give you a higher salary than the theoretical studies. And the effect of sex is completely gone. It's 4,000 plus minus almost 4,000. The p-value is 0.2, which tells us that the apparent difference in salaries between males and females are not actually due to sex, they are due to other variables. One thing you should do in models like this is to try to reduce number of variables or predictors. In particular, you should remove correlated predictors. If you look at the years of service versus years of since PhD, obviously these two variables are correlated. Typically, there will be some people which have more years since PhD than years of service because they were employed by this university a bit later in their career. But there is a strong correlation between these two variables. And the library CAR contains a very useful function which you should use with your models. It's called VIF. It's about variance inflation factors. It measures how much a given variable is explained by others. If we apply our full model here, we immediately see that the variance from years since PhD and years of service are much larger than other variances. They are 7.5 and 5.9. This is because of the fact that years since PhD can be explained by years of service. These two variables are correlated and hence redundant. Then, if we remove one of these variables because we call it redundant, and we have a reduced model without years of service, this is what we get. Variance inflation factors are now much smaller. Ideally, they should be close to 1. Now we can use a reduced model. So first of all, we have a multivariate model containing all the variables, but then we decided that one of these variables is strongly correlated with others, and we removed it. So we have now rank, discipline, years since PhD, and sex. And this is the result. And again, the effect of the rank of professor is very strong. Professors earn much more money, and the effect of sex is essentially gone. Why is that so? Well, if someone asks you based on these data, is there a gender gap in this particular college? And the answer would be, well, despite the appearances, there isn't an explicit gap. At the same rank, men and women earn the same salary, which is nice. However, there is a serious deficiency of women in higher ranks. This plot shows the proportion on females in different ranks: assistant, associate, and full professor, with 95% confidence intervals. This is the 95% confidence interval of a proportion. Among lower ranks, the proportion of females is about 15, 16%, which is already quite low. But in full professors, as you progress in academic scale, there are fewer women. And this is the problem. It's not that the salary for male and female professors is different, it's the same. There are just fewer females at higher ranks. And that will be the answer to this question. And this is a demonstration how a linear model, a proper multivariate linear model, can be used to answer certain questions. Thank you. This is everything for today.